So to calculate velocity by knowing height, we're going to assume that the system is isolated and there is no friction. So we need to start by calculating the gravitational potential energy at the start, so at the top of the path. And we do that by multiplying the mass of the object times gravitational acceleration times the height of the object. Energy is conserved, and so the gravitational potential energy at the top is going to be equal to the kinetic energy at the bottom of the path. So GPE top is equal to KE bottom. We know this because if energy is conserved and there is no friction, then there's only going to be potential energy and kinetic energy. And so all of the potential energy at the top will get converted into kinetic energy by the time the object reaches the bottom of the path. Next, we use kinetic energy equals 1/2 mass times velocity squared, and we plug in the gravitational potential energy amount that we calculated from the start of the fall. When we rearrange the formula, we can solve for V, and we get a formula of the square root of 2 times that kinetic energy divided by the mass of the object. Now, there is a much easier way to do this. So if we set the formulas equal to each other, so again, potential energy at the top of the path is equal to kinetic energy at the bottom of the path, we can cancel mass from both sides of the formula. After that, we multiply both sides by 2 to get V by itself. And now we take the square root of both sides so that we can get V from V squared, and we end up with V equaling the square root of 2 times gravitational acceleration times the height of the object. Now you might have noticed that mass is not in this formula, and mass doesn't actually matter, so it doesn't need to be. Remember that gravity accelerates any and all mass at the same rate, and here on Earth, that average rate is about 9.8 meters per second squared. Things fall differently because of friction, from air resistance, for example, or contact with the path. So a ball and a feather dropped aren't going to fall the same way because of air resistance. A roller coaster isn't going to go as fast as it possibly could because there's going to be some friction between the coaster and the track. We can get a very close approximation of velocity, though, and this formula works on any mass to do that. Let's do an example. The roller coaster cars shown here are 60 meters above the lowest point on the track. How fast is it moving when it reaches the lowest point? Assume that there is no friction. So using this formula, we plug in the values that we know, 9.8 meters per second squared for gravitational acceleration, and 60 meters of height, and we get a velocity at the bottom of that track of 34.29 meters per second. Now again, don't forget friction in the real world. Remember, we are assuming an isolated system and no friction when we do these problems, but in the real world, it doesn't happen so simply. Our calculations will be close, but they're not going to be exact.